video we will see a problem on direct and bending stresses, where we have to find the stresses on all the four corners. Here is the question we have. A square column of size 400 mm into 400 mm is subjected to an axial load of 400 kN. In addition to this, a load of 400 kN, 40 kN acts at an eccentricity of 20 mm about both axes, that is xx and yy. Find the stresses on at all four corners. So this is the question we have. Whatever is given here, I'll write that in the form of data first. So let us get started. Here we have square column of size 400 into 400. So the area is given. That comes out to be 160 into 10 raised to 3 mm square. Then it is subjected to an axial load of 400 kilonewton. This is the load which is passing through the axis. I'll give it as P1. Next, in addition to this, a load of 40 kilonewton acts at an eccentricity of 20 mm. So we have one load which is passing through the axis. Another load of 40 kilonewton acts at an eccentricity. So this is the eccentric load. So here I'll denote it as P2 as 40 kilonewton. Acts at an eccentricity. So here I'll write down eccentricity E as 20 mm about both xx and yy axis. So it is ex and ey. Both are having the same value of 20 mm. The question is to find the stresses at all four corners. So here we have the question. Now with the data available, let us try to get the solution to this question. Now in the solution part, the first thing is to draw the diagram. Here there is a square section given. This is the square section, the dimensions are given. $400 mm is the width. 400 mm is the depth. Now, after we have drawn this square, I'll name all the four corners. A, B, this corner is C, and here we have D. So these are the four corners. And after drawing this square, here we have to calculate the stresses at all four corners. Now after this, now here we have the horizontal axis xx and yy for the given square. I'll read the question. In this, what is given, that area of the square we have found out. Now load P1, it is given that a square column of size 400 mm into 400 mm is subjected to an axial load of 400 kilonewton. It means on the axis we have P1, that is the axial load. Then it is given that in addition to this, that is in addition to 400 kilonewton, there is a load of 40 kilonewton which is acting at an eccentricity. So 40 kilonewton acts at an eccentricity of 20 mm about both the axes. So Ex and Ey is 20. So here I'll say that I'll even draw the diagonals. Here we have one diagonal AC. and the other one is BD. So I have drawn the two diagonals. Now here the load is eccentric with respect to x and y at 20 mm from both the axes. So if I take this x-axis, from this the distance is 20, and even y, from y the distance is same. So here I'll say that this is the location of load P2, which is the eccentric load, and its eccentricity is given. This is with respect to x, so Ex, and here is the eccentricity with respect to y, so Ey. In this problem there are two loads. One is the axial load, other is the eccentric load, as is visible from the diagram. The next thing, the question is to calculate stresses at all the points. So here I'll say that after this. Now if we look into this, here I'll say that since because of axial load there will be direct compressive stress in the square section. So therefore here I'll find out direct stress. Direct stress is given by sigma d is equal to, because of P1 there is axial load, so P1 upon area so here therefore sigma d is equal to P1 is 400 kilonewton. Now after this, because of P1 there is direct stress. Now if I look at P2, because of this also there is direct stress, because that will result in compression of the member. So here I'll write down it is P1 plus P2, and because of that there is direct stress. Since P1 is acting at the axis, so compressive stress, even P2 is acting in the downward direction, so again compressive stress. So P1 was 400 into 10 raised to 3, P2 is 40 into 10 raised to 3, area 160 into 10 raised to 3. So from this I'll get direct stress. I'll write the answer onto the next page. Therefore direct stress is 2.75 Newton per mm square. Now after getting this direct stress, we need to calculate the bending stress, and by looking into the diagram we can say that because of P1 there will only be compressive stress because it is axial, whereas because of P2 there will be both the stresses, compressive as well as bending. So when we are considering bending, at that time we have to take load as P2, and here if we see from this point the load is eccentric at this much distance. So here this is the eccentricity of the load, and this eccentricity I'll denote it by small e, and for that eccentricity we can calculate it. I'll draw the diagram. Now from the geometry of figure alongside, now here is the figure which I am drawing. This is 90. Now here is the eccentricity E. Ey value is the horizontal value. Here I am drawing this triangle, this small triangle I have magnified here. So here the value is This is 20 mm, and even the value here is 20, and this angle is 45 degree, exactly through the half, because it is on the diagonal. So this angle would be 45 degree, half of 90. Now I'll say that from this geometry, that since we want to know E, so we can use either sine or cos formula. So if I use sine 45, that is opposite side upon hypotenuse, which is E. So therefore E is equal to 20 sine 45, and my answer is 28 point. Therefore E will be, E I shifted here, so this 20 sine 45 will not be there in the numerator, it will be there in the denominator, because here I am shifting E here. So 20 upon sine 45, and the answer is 28.28 mm. So I have found out the eccentricity of the load, which is the eccentricity on the diagonal. Now I'll calculate the length of each of the diagonal, that is either BD or AC. So if I look at this triangle BCD, here BD is the hypotenuse. So again I'll say that from the geometry of figure, here we have BD, this is 400 mm, even here it is 400 mm. So BD is the hypotenuse. So now from the geometry of this figure, BD is the hypotenuse. So by Pythagoras theorem, BD is equal to root of 400 square plus 400 square. So here I'll get my answer of BD. I'll write it here onto the next page. It is 565.69, and since it is a square section, so BD and AC both will have same value. Now after reaching here, next step is we would go on for the calculation of bending stress. So here I'll say that therefore bending stress is given by sigma B is equal to m by z. I'll keep this as the first equation. Now I'll go for the calculation of bending moment. Therefore bending moment is given by, now bending is only about, or we can say only because of load P2. Since P1 was axial, so because of P1 there is no bending, there is only compression. But because of P2 there is compression as well as bending. So here I'll write down bending moment is P2 into the eccentricity. We have found out this is E, so P2 into E. Now P2 value, that was 40 into 10 raised to 3 into this eccentricity we have calculated just now. Its value is 28.28 mm. So bending moment comes out to be 1.13 into 10 raised to 6 Newton mm. Now after getting the bending moment, we require Z. Z is called as section modulus. So therefore section modulus is given by Z is equal to I upon Y. keeping this as the second equation. Now I'll go for the calculation of I, which is very important here. I is called as, therefore, I is moment of inertia about diagonal BD is given by. Here if we look into this problem, the eccentricity is measured with respect to diagonal. So whenever we have eccentricity with respect to any of the axes, we calculate the mi about that axis. Here the eccentricity E is with respect to diagonal BD. So I am calculating mi about BD. So I'll say that therefore mi about diagonal BD is given by I suffix BD is equal to, now that is 2 into the mi of triangle ABD about the base. Now what is this? For that I'll draw the diagram here to explain it in a more simple manner. This is triangle ABD. Triangle BCD. Now here we want to calculate the moment of inertia about BD, this diagonal, but this diagonal is passing through the right angle triangle ABD and through the right angle triangle BCD. And for both these right angle triangle, here BD can be considered as the base and this would be the height. So here I'll denote this point as M. A to M is the height. So for this case, for calculating the mi about BD, I am considering the moment of inertia of a triangle and multiplying it by 2. So here same thing I have written. I will be calculating the moment of inertia for this triangle about the base BD. Similarly for this triangle about the base, multiplying it by 2 simply because both the triangles are having the same dimensions. So if I find mi about any one triangle about the base, simply I have to multiply it by 2. So therefore here I'll write down IBD is equal to 2 into, now moment of inertia formula for the triangle about the base, it is given by BH cube by 12. We have three different moment of inertia formula for the triangle. If it is about the base, it is BH cube by 12. If it is about centroid, then it is BH cube by 36. If it is about apex, then BH cube by 4. So here since it is the centroid, it is passing through the base. Here I am writing it as BH cube by 12. Now the distance is A to M, which is considered as the height, and this is the base, which is BD. So I'll say that therefore I suffix BD is equal to 2 into the base is BD, value was 565.69, and now this height AM, I'll calculate it at the side. AM, as we see, it is half of AC. AM is half of AC, and what is AC? It was equal to BD, that is AM is, BC was 565.69, so divide that by 2. So AM answer, it comes out to be 282.85 mm. So this AM is nothing but small h, which is the height of the triangle. So here I have 282.85 cube divided by 12. So after calculating this, I'll get I suffix BD. My answer is 2.133 into 10 raised to 9 mm raised to 4. Now I have calculated the mi value, that is IBD, about the diagonal. Since I have calculated about the diagonal, the distance of this diagonal with respect to the corner, this would be the value y. So it will be half of AC. So I'll say that therefore y will be half of AC, or even if we take half of BD, that is also correct. So here AC was 565.69 divided by 2. Y comes out to be 282.85 mm. After getting I and Y value, we can put them in equation number second. So therefore, put I suffix BD and Y in equation number second. So now, when we are substituting the value in equation second, we have Z is equal to I by Y. Z is equal to I, which is 2.133 into 10 raised to 9. The value of Y, 282.85. So from this, I'll get the answer of Z, which comes out to be 7.54 into 10 raised to 6 mm cube. Because this is the section modulus, it is moment of inertia, the unit of moment of inertia mm raised to 4 upon y is the distance in mm. So here we have mm cancel, that is mm cube is the unit of section modulus. Now after getting section modulus, I'll put the value of m and z in equation number 1 to get the bending stress. Therefore, put m and z in equation number 1. So therefore sigma b is equal to m was 1.13 into 10 raised to 6. Z we have found out just now. Z was 7.54 into 10 raised to 6. So from this I'll get the answer of sigma b, and it comes out to be 0.15 Newton per mm square. After getting the direct stress and bending stress, now we can go for the calculation of stresses at all four corners. So starting from point A, because that is asked in the question. So now, since stress at corner A, that is sigma suffix A, that will be direct stress plus bending stress. Why? Because here direct stress would be acting on all of the corners, but bending would be at that corner which is closer to the load. As we see here, the corner A is closer to the load, so there will be bending on this. So it is sigma D plus sigma B. Sigma D, it was 2.75 plus sigma B is 0.15. So therefore stress at A is equal to 2.90 Newton per mm square. And this is the only chapter in which we are taking the positive value as compressive stress. So the stress nature is compressive. Then stress at corner B. Now if we look into the diagram, here the eccentric load is on this diagonal AC, and since the eccentricities are same, so the effect of P2 will not be there on B and D. So B and D would be subjected to only direct stress. So here I'll write down sigma B is equal to sigma D, value is 2.75 Newton per mm square. And again, as this is positive, it is compressive stress. Then stress at corner C, now sigma suffix C, it will be for corner C, as we see the load is closer to A, far away from C, so it will be sigma D minus of sigma B. For A it was plus because the load was closer to A. So here we have 2.75 minus 0.15 and that gives me the value as 2.60 Newton per mm square, and this is positive, so compressive. Now stress at corner D, that is sigma D, again the effect of P2 will not be there on D as it was not on B because it is lying on the diagonal AC. At the same time eccentricities are same. If the eccentricities would have been different, then there would have been effect on B and D as well. So here sigma D is equal to, directly it is the direct stress, and the answer is 2.75 Newton per mm square. As this is also positive, so here we have compressive stress. So here if we look into the problem, the question was to calculate the stresses at all four corners, and we have found out all the values, all are compressive, and with this we complete the problem.